Welcome to the 13th lecture. We are studying stochastic processes and continue studying we will continue studying Markov processes. In lecture number 12, we studied an introduction of Markov processes. In this lecture, we will study transition probability matrix. In last lecture, we studied transition probability graph, which we also call Markov chain. There is a small recap before we go ahead. The recap is that for any discrete times, the probability that at time n plus 1, the process takes on value j, given all this all this past stuff is dependent only on the recent past and is not dependent on these far past events, right? So it's a process which can take on a value at any time interval, but the value it takes on at any time interval n is dependent on what has happened at n plus 1, but is independent of all previous events. So this is a small recap, and we call this as a transition probability Pij. This is the probability that from any time Tn, if we move to Tn plus 1, the probability with which the state I is transformed into J at time n plus 1, the new state is J with probability Pij, given at one previous time interval the state was I. So at next time interval it is J, the probability is P sub ij, right? The same information that we encoded in a Markov chain or a transition probability chain in our last lecture can be written in terms of a matrix. Here it is a transition probability matrix written for a process which has m states. So this is the probability that in a future state, the process moves to state number 1. This state, given it was at state number 1 in the previous time interval, right? And at time n plus 1, this is the probability that will move to state number 2, given it was previously at state number 1. And this is the probability that will move to state m, given it was initially at 1. So this is an m cross m matrix for a Markov process governed by a chain with m states. The probability matrix will be an m cross m matrix. So TPM is always a square matrix. It is always a square matrix where sum of each row is equal to a 1. You see the sum of this row is a 1, of this row, and for all rows it's a 1. So the summation Pij is a 1 for each row. Here is an example that Abdul Wasim is a student. He is taking our stochastic processes course. If he is up to date in a given week, he is up to date in next week too with probability 0.8. But if he is not up to date, he is behind this week, he will be up to date next week with probability 0.6. So we need to compute its matrix, transition probability matrix, and transition probability graph. So this, let's call this up to date as state number 1 and this behind state as 2. So if he is up to date in this week, he is up to date in the next week with probability zero point 0.8. So it is 0 0.8. If it is zero point 0.8, he is behind in the next class with probability 0.2 because sum of all arrows emerging out of a state should sum to 1. But if he's behind in this class, he is up to date in next class with probability 0.6. It's given. This means that he is falling behind in the next class he is behind in the next class with probability 0.4. So P11 is 0.8 is 0.8. P12, the probability of going from 1 to 2 in the next time interval is 0.2. Probability of 2 1 is 0.6, and from 2 going to 2 from 2 is 0.4. So the same information, because we know we have P11 here, P12 here, P21 here, P22 here. So we put 0.8 here, P12 0.2, P21 0.6, P22 0.4. So we will keep on studying Markov processes in our upcoming lectures. Thank you.